Hi everyone, in this video I'm looking at the very last part of question 16b from the Baulkham Hills Extension 2 trial exam from 2020. So I've already worked through part 1 and part 2 in separate videos, so definitely take a look at those if you haven't already, because we're going to rely on those results for this part 3, where we're asked to prove by mathematical induction that an is greater than or equal to gn. And that's for n being in the positive integers. Now, the word hence there kind of lets you know you're going to have to rely on what we've just proven. So this is kind of where the question's been leading to. As I mentioned in the prior videos, it's basically a setup to help us then eventually prove effectively the AM-GM inequality, or the arithmetic mean geometric mean inequality, which is a good proof to be able to do because it's a really handy result to use in other problems. So yeah, let's take a look. So this is what we need to prove. We're told to use induction, so let's just follow the steps. Step 1 is to show that in this case our inequality will be true for n is equal to 1. So let's have a look at our left hand side, which would be A1. And capital A1, according to our definition, if we just come back right to the beginning of 16b1, would be just A1 on 1. So that's going to be A1 on 1, or just A1. Now the right-hand side would be equal to G1, which would be just A1 to the power of 1 on 1, and that's also going to be A1, which is, technically is less than or equal to the left-hand side, because in this case we've got equality. So therefore we can say that it is true for n is equal to 1. Now step 2 would be to assume true for n is equal to some integer k. So what we're saying is that we're going to assume that ak will be greater than or equal to gk. And you kind of know, or you hope at least, that when you get to step 3 you can find some kind of link here. So now let's go to step 3, where we want to show true for n is equal to k plus 1. And I think it's at this point that we're going to start to make our linkages to the prior questions. And I think it makes sense that we go right back to what we proved in part 1, and we make use of this inequality. So let's say from part 1 we know that, I should have held that there, we know k plus 1 times a k plus 1 minus g k plus 1, that is going to be greater than or equal to k times ak minus gk, ak minus gk. But remember, that's if there was a condition on that. That condition was if lambda k to the k plus 1 minus k plus 1 lambda k plus k is greater than or equal to 0. So that was the condition. This first inequality was only true if this second one was true. But we can say from part 2, we can actually say, well, we've proven that for x positive, it is the case that x to the k plus 1 minus k plus 1 x plus k will be greater than or equal to 0, because we worked through the steps to prove that. And so that's kind of what part 2 was all about. It's so that we could say, well, this condition is going to be true for lambda k positive, and the way lambda k is defined, it will be positive because we've got a, which we were told right at the beginning are positive numbers, and then the geometric mean is going to be positive, so lambda k is going to be positive. So we're in safe territory here. So from part 2, it is the case that lambda k to the k plus 1 minus k plus 1 lambda k plus k is greater than or equal to 0 for lambda k greater than 0. So therefore, we can make use of this inequality. So so I guess we can just start making use of it. So we can say therefore k plus 1 a k plus 1 minus g k plus 1 will be greater than or equal to k a k minus g k. Now it's probably say a good idea to bring our k plus 1 over, because we want to eventually get a k plus 1 greater than or equal to g k plus 1. This is kind of what we're after. We want to just say that's greater than or equal to 0 so that we can then bring the g k plus 1 over. So let's get it by itself to start. So let's say a k plus 1 minus g k plus 1 will be greater than or equal to k on k plus 1 a k minus g k. Now this is where we can link to step 2, because if a k is greater than g k, then that really means if I bring the g k over, a k minus g k will be greater than or equal to 0. So I know this bit is greater than or equal to 0, and I know this bit is greater than or equal to 0 because k is a positive integer. So a positive integer divided by a positive integer plus 1 will also be greater than or equal to 0. So maybe I'll turn over at this point. So we can say therefore a k plus 1 minus g k plus 1 will be greater than or equal to 0, since k is in the positive integers and ak minus gk is greater than or equal to 0. So therefore ak plus 1 is greater than or equal to bringing over the gk plus 1. And that's it. So we say therefore true for n is equal to k plus 1. And so now we can make our final inductive conclusion. I'll just write by induction, because that's how I do it to be lazy. But ultimately, if you've learned to write out the full spiel, feel free to do that. But I'm just going to say by induction, an is greater than or equal to gn. Or in other words, the arithmetic mean is greater than or equal to the geometric mean, which, as I've mentioned a few times, is a really handy solution to know. So it's never hurts to be able to prove it. Boom! And there you have it for that question. That's the final part of question 16b, which itself was the final part of that whole trial exam. And as I mentioned back in the first video for 16b part 1, these trial exams, often they can actually be harder than the actual HSC, especially at these selective schools where I guess when they're thinking about scaling and all that kind of thing, they want to really set quite difficult internal assessments to really get the whole class sharp so that they then, I guess, outperform the wider cohort across the whole state, and therefore the scaling will work favourably for them. So yeah, I always say if you can tackle these selective school trial exams, then you're looking pretty good to do well on the final HSC. Hopefully for this question, everything I worked through made sense, and you know, you're able to follow along. And yeah, tick boom.